So we have this calculus, the decimal calculus or the Newtonian calculus. So what this calculus is all about. There are many ways in which we can kind of approach to the things that exist in nature. One of the philosophical problems with mathematics is that sometimes you have mathematical theories, but those theories are sitting on some what you call unrealistic kind of assumption, or axiomatic. So it has axiomatic foundations, but those axiomatic, those axiomatic things doesn't exist in reality. For example, if you talk about the geometry that we do in plane, or the geometry that you might learn in your school level, so you learn, what do you call Euclidean geometry. This geometry done by Euclid, it doesn't exist in nature. In other words, so what Euclid did, so he took the geometry and tried to fit it on the nature. So why it doesn't exist in nature? Because what Euclid assumed that there are things called points, and there are things called lines, straight lines, and there are things, planes, there is in three-dimensional space. But the fundamental question is, does this point exist in reality? Or can you have a pure straight line? The answer is that a pure straight line only exists in our head. It doesn't exist in reality. So nothing is purely straight. Okay, you can't show me and point to something that, that thing is a straight line, that line is a straight line. So that thing doesn't exist in reality, it just exists in our head. Similarly, the calculus, so the Newtonian calculus has a lot of interesting aspects. Okay. One of the interesting aspect is are the fundamental assumption on which the entire calculus is sitting, the Newtonian classical calculus is sitting on, is that you can infinitely slice the things actually. Okay. So in other words, when you're saying that you can have infinitesimal set, okay, so you have this, this curve, and you can compute the area by, splitting it into, really small sub-intervals and making rectangles into much bigger things. So in other words, if you want to, compute the volume of a nonlinear object actually, a three-dimensional object, then you assume that basically you split that three-dimensional nonlinear object into small cubes, PEs actually. Small cubes, infinitesimal cubes. So when you are splitting a physical object into an infinitesimal cube, or we are splitting an interval or a short span of bunch of number into infinitesimal parts, lots of infinitesimal parts, you are assuming implicitly that we can slice things infinitely. Okay? So you are assuming it. Okay? And unfortunately, that so like this is far from reality. Because what is infinite? Still trying to figure it out. What is infinite? We have infinite answers. So in other words, all these theories have foundational assumptions. Okay, those assumptions are the assumptions on which the entire theory is built upon. Actually, what the Brownian calculus assumes is that, somehow nature is following this, what you call, deterministic patterns actually. So what do you mean by determinism? Yeah, deterministic things. So you have these essentially two approaches, deterministic and stochastic actually. Okay. So what do you mean by deterministic? So what essentially we say that if you have a soccer ball or football and you kick that football, okay, and if you know the initial velocity and the angle, with what you have hit the football, okay, you can almost know everything about that football, okay, how high it is going to go, how far it is going to go, when it's going to the top line, when it's going to hit the ground again, and you can almost, in other words, you can model the dynamics of this soccer ball using a very simple, what do you call it, differential equation or a calculus tool. Okay. But we assumed it to be deterministic. Deterministic. In other words, what do you mean by deterministic? By determinism or deterministic evolution actually is that if you roughly know that how it started, you can always approximate that, okay, what would be the behavior of this evolution at a given instant. So you can always kind of predict it. So I know that the day is coming after the night and the night is coming after the day actually. So in other words, you have your calendars and you have very precise what we call descriptions that when the sun is going to rise, at what precise time, and when the sun is going to what we call when the sun is going to go down. So we can calculate this precise time. Because we assume that all these things are deterministic. And I'm not saying that it's a bad model. These models are very good models actually. So they have okay, the whole of what you call the industrial revolution has happened. This technological revolution has happened because of this what you call the Newtonian calculus actually, or this deterministic calculus. Okay. So I know that this Euclidean geometry, okay, that we have, it works very well. It gives a lot of answers. But we know that this Euclidean geometry is based on some of the assumptions which doesn't exist in nature. So similarly, we know that Newtonian calculus works well. Okay? It can give very good approximations. Okay? It's very successful in describing a lot of things. Okay? One of the miracle that Newtonian calculus is doing is this, what you call theory of general relativity, which is telling you almost everything about the macroscopic universe. Okay? So it's a successful theory. But the issue is that we know that in general things are not deterministic. Okay? And you can treat this as a challenge from my side, that try to come up with a purely deterministic example that exists in the nature, a process that is deterministic and exists in nature. Okay? You will see that it's pretty hard to find. You always have an ambiguity. In other words, when we say that we have a model for the soccer ball, the movement of the soccer ball, we are ignoring a lot of things. Okay? We are ignoring that okay, there is only one force acting on it. Yeah, so there could be a resistance. Okay? There could be a lot of other factors actually. In what medium you are, what do you call throwing that ball? Medium matters actually. So in its essence, one challenge for you is to think of a process for which you can put finger and say that okay, this is a pure deterministic thing actually, and this you don't have any kind of what do you call randomness. Okay, and I'm pretty much sure that it's a very difficult to spot purely deterministic. So you always have randomness. And what do we mean by randomness? So, and why we have randomness? Or how the randomness can emerge actually. So you have on one side you have these all deterministic processes or deterministic phenomena, but as I said that it's pretty difficult to find a pure deterministic example. But if things are not deterministic, then what they are? So we say that they are basically stochastic. And by stochastic I mean that there is a kind of a randomness in them. Okay? And by randomness, what we mean? So randomness is not just that, okay, you have this coin and you are flipping it and you are getting the random answers. Randomness can emerge due to a lot of reasons. Okay? So it could emerge due to, for example, lack of information. Okay? Lack of information. Sometimes you do not have an information about a thing, and that thing is kind of, has a random nature for you. For example, okay, imagine that you go outside and go to the bus stop and wait for the bus. Okay, if you don't know the schedule, if you are lacking the information, okay, what you're going to assume? You're going to assume that the bus is going to come at the random time. So in other words, lack of information is giving rise to what is called randomness. Okay, you can assume that. I mean, if you know that, okay, if you know this schedule, actually, that this randomness goes away. So in other words, you will see basically throughout the course that there are a lot of phenomena that exist in nature, in which there is involvement of the randomness. Okay? But that randomness is coming out of different reasons. Okay? So it's not like just jiggly behavior of a particle, okay? But you can have randomness due to several reasons. For example, I gave you one example of that sometimes we have lack of information, and that kind of creates a random process for you, or a random situation for you. Okay. So what we want to do in this course is that we want to, have a transition from this deterministic calculus to a more powerful and a more general kind of a calculus. Okay, it's called the stochastic calculus. Okay, and why this is important? Now think about it. You have this geometry, for example. Okay, the geometry so far what we have learned, it was based on the Newtonian calculus. So we're using these multivariable calculus knowledge to make the computations. Okay? But if we know that we have a more general and a more better calculus actually, okay, which can not only do the things which deterministic calculus can do, but it can offer something additional actually, that it can offer you. It can offer you that when things are not happening in a deterministic manner, you can still understand. Okay, so you have geometry, so you have a stochastic geometry. Okay, you have engineers do signal processing, so these days you have stochastic signal processing. Okay, physicists do you have quantum mechanics. Okay, you have what we call stochastic quantum mechanics. In other words, the many of things, okay, which exist in deterministic fashion are being generalized to its stochastic case, and which is kind of more natural and more reliable than calculus. Okay. That's what we want to do. We want to transition ourselves from Brownian calculus, deterministic calculus, to this random calculus actually. Let me begin with one motivatory example. Okay. Example could be, okay, so before getting into it, what texts we are going to follow. Okay? So the key text that we are going to depend on is one of the. Okay, there are a number of basically texts. Basically, you can follow anyone. But for this course, I will highly encourage you to follow this book by Stochastic Calculus for Financing. Okay? You will find a very little finance in it, a very rigorous version of Stochastic Calculus for it. It's a book by Thomas. Okay? That's fine. It's a very, very good introduction. Okay. And that's the market. This is one of the important book that we are going to follow. The other book that I like as a introduction book from Calculus is introduction to stochastic integration. Introduction to stochastic integration. It's a very nice book. I think the name of the author is who I. Friends and descendants of Ito. Ito was one of the initiators of this study in the Japanese guy. And the paper that he wrote on basic definition of stochastic integration, in my opinion, it's one of the most cited paper in the history of empirics. No other paper has been cited more than that. I could be wrong, but if you can show that this is one of the highly cited papers of that. So that's the second bit. We're going to switch between these two books. Okay. There are a lot of other texts also available. Okay. For example, one of the all-time favorite book, Basic Stochastic Process, by my supervisor, Girsanov. Okay. It's also a nice book. So, there are lots of texts. The other, kind of more rigorous book is by. So we treat them as reference books. Sometimes you read a notion and a concept from one book, you feel that okay, it doesn't make sense to me, so you can switch to other and then switch to other. So all these people have different ways to describe the same thing. Another, beautiful book, an introduction to stochastic differential equations. Lawrence C. Evans. This is also a very nice introduction of it. That's a classical one. If you ask me which is the access to stochastic calculus, the introduction to stochastic calculus, you always hear Evans coming out of it. Evans is also a very question for equations. Stochastic differential equation as well. So I want to try this book, Stochastic Calculus for Finance. I'm pretty sure that to be a good book. It's rigorous and its language is friendly, it's student friendly. Also, we have a good time with these two books by Thomas and by stochastic integration. close to most. That's a bit about it. So why is stochastic calculus? So let's begin with what I just said. Okay, this introductory part will be kind of more formal, not rigorous actually, more formal or heuristic. Okay, it's going to be more formal. The things that I'm going to say, I'm not going to do this. So just want to give you the view that why this calculus is important and what else all represents, and then we'll get into the theory of calculus. Okay. So imagine you have a particle, okay, and this is the trajectory of the particle. Versus x-axis, okay, and at naught, the particle has this position x naught, okay, while this trajectory, this smooth trajectory is we call x of t. Okay. In other words, what we are assuming that this particle has such a smooth displacement path. Okay, but think about that. Can something have a really smooth displacement? The answer would be purely no. Imagine a bird that is flying at you. Right? And imagine that you are tracing the movement of that bird. So would you expect to get a smooth curve out of it? Okay. Just imagine, the way, for example, a car is displaced on, what do you call, on the road. So would you assume that the car will always go onto the road, with one-dimensional speed? It's not going to happen. You experience it. You must have experienced it that, your drive would be always interrupted, okay, by a lot of trucks and other buses and cars actually. So you want to go with a smooth speed, but so after some time when a truck is coming, so unexpected motorcyclist is coming, so you have to change your speed at the random times at the random place. So in other words, what we do in Newtonian calculus, we assume that everything is smooth. Okay. Now, how you can get this trajectory? Okay, so you have, in order to get this trajectory, you have what we call Newton's law. You just have to write a differential equation, okay, to get this trajectory. In other words, you can have. So imagine x naught is something in Rn. We are in n dimension. Okay, and the evolution of a particle that has such kind of trajectory can be written by, for example, a stochastic differential equation. X of t is equal to v of xt subject to the initial condition of the initial what we call displacement of level that we want to interpret as x naught, where v is a vector field from Rn to Rn. Okay. So that's how we assume, okay, that a bird is going to fly. But if you come up with the experimental data, really the experimental data, if you take a real bird, okay, and put a tracker on it, okay, and try to trace, the curve that it follows, okay, what do you think? You're going to get something like this. You're going to get something like this. You're actually going to see that you're going to get something like this, actually. Okay, something like this. Okay. Sometimes the bird is going down and taking speed, it's going down and taking speed, and so on and so forth. So you can plot it out. Anything that you can. So this. Okay. So that's what I'm trying to justify. That's what I'm trying to justify, that why I need this stuff. So this is something that exists in only our head. Okay? It doesn't exist in reality. But when you will collect the real experimental data, you should get some